Jnanam paramam dhyeyam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. We have been discussing half sandwich complexes of the type transition metal arene carbonyl complexes and their reactivity in the last lecture. And with that perspective, we have seen that these transition metal arene metal carbonyl complexes are quite significant in number. We had seen various of them which exist, and then we have looked into their preparative procedures as well. One of the most common procedure which often are used for making this half sandwich transition metal arene carbonyl complexes is the carbonyl substitution reaction of metal carbonyls with arenes at high elevated temperatures. So, this is by far the most direct method for synthesizing this arene metal carbonyl complexes, and continuing upon that discussion, we are going to take a look at few other methods which are available for synthesizing these transition metal arene carbonyl complexes. And the next reaction that comes to the mind with regard to preparation of these complexes is the direct reaction of metal carbonyl halides with arenes in presence of AlCl3. So, metal carbonyl halide plus arene plus AlCl3 MnCO5 Cl plus benzene in presence of AlCl3 gives 2 carbonyl to give this benzene MnCO CO and AlCl4 minus anion. Here this AlCl3 can be perceived as something which is abstracting a chloride, creating a vacant site, and then 2 other carbonyl gives way to this incoming arene, which is 6 electron donor, resulting in this benzene manganese tricarbonyl cation with AlCl4 anion. The next, of course, comes these aryl substitution reactions or the ligand exchange reaction or arene substitution. The reaction is illustrated by a few examples given over here. This is the direct reaction of arene chromium tricarbonyl plus another arene which is given by arene dashed at 140 to 160 degree centigrade, giving arene dashed chromium tricarbonyl plus arene. The next reaction is CH3Cn whole 3 chromium tricarbonyl plus arene at 25 degree centigrade, giving Arene chromium tricarbonyl plus 3 CH3 CN, and the last one is tripyridine PY3 molybdenum tricarbonyl plus Arene in presence of Et2BF3 salt, giving Arene molybdenum tricarbonyl plus 3 PYPF3. So, this seems like quite a more general reaction, in the sense that there can be direct substitution of an arene with another arene, or it can even be a substitution of coordinated acetonitrile with arene, or it can also be substitution of pyridine with arene by treatment with BF3 ferrite. So, this arene substitution reaction seems more like a general reaction. Now, regarding the structure of these arene metal carbonyl complexes, it is important to note that quite a wide variety of structures have been reported for these kind of complexes. By wide variety, I mean that these arenes in arene metal carbonyl complexes have been found to be coordinated in a eta 6 fashion, or even eta 2 fashion, to two different metal center, or even to eta 3 fashion, eta 2 fashion to 3 different. So, metal centers, giving rise to dinuclear as well as trinuclear complexes. I am going to talk about some of the interesting ones that have been structurally characterized as representative examples of the same. For example, this benzene tricarbonyl chromium which is 140 picometer is the carbon-carbon, and this distance between the benzene and the chromium is 172 picometer. Chromium carbon distance is 184 picometer, and carbon oxygen is 114 picometer. Here is a another. So, this is a like a piano-stool structure. Another dinuclear compound is this rhenium dinuclear compound with 2 arene rings, where one of the arene rings is eta 6 coordinated, the other arene ring is eta 2 coordinated, and this is a beautiful structure. As I will be saying, this is with pentamethyl CP. Rhenium carbonyl with one of the benzene ring being eta 2 coordinated, and the other benzene ring be also in a eta 2 coordination fashion. Bound to this pentamethyl cyclopentadienyl ligand, and then 2 carbonyls. So, here we see a diversified a new kind of binding, where this arene moiety is bound in a additive fashion to one metal rhenium and additive fashion to another rhenium. So, giving this dinuclear structure. Here is also a trinuclear structure. This is also a very interesting example in which the rhenium is bound to 3 osmium centers in a trinuclear fashion. Okay. And the binding is shown in blue. Which is shown over here. So, this is a very interesting example, where this rhenium is bound in a additive fashion to 3 different metal center. Now, what is interesting about these examples is the fact that there is a wide diversity of binding of this arene ring to the metal in this arene transition metal carbonyl complexes, and it can vary from the more conventional eta 2 6 type arene complexes to eta 2 dinuclear to eta 2 trinuclear metal carbonyl complexes, as is shown over here. Now, then comes the interesting aspects for these complexes, and it is the fact that these the reactivity pattern of these metal aryl carbonyl complexes. So, we are going to discuss this in bit more details by looking at the structure, and there has been convergence on the type of reactivity these arene metal carbonyl complexes show, depending on the part of the arene ring which is one looking at. So, I will illustrate this with this beautiful example. For example, this arene C H X C H X, this kind of structure bound to chromium tricarbonyl. So, these halides, the position in alpha and the beta positions, they undergo ready solvolysis, or these are the regions which shows enhanced solvolysis. Similarly, the protons over here shows enhanced acidity. These benzene ring shows enhanced nucleophilic substitution. So, this ring undergoes nucleophilic substitution reaction, This proton shows enhanced acidity, and this underneath the benzene ring and that metal tricarbonyl undergo enhanced or steric hindrance. So, as a consequence of this enhanced steric hindrance, one sees in many occasions the attack happening from the exophase of the Arene ring as opposed to the endophase of the Arene ring. So, with this reactivity scheme put in place, let us take a look at some of the reactions which these Arene chromium tricarbonyl complexes that exhibit. So, the first and foremost is the electrophilic substitution. Now, this electrophilic substitution in Arene metal carbonyl complexes is lower in reactivity than that of free benzene. Reactivity is lower than in free benzene, free Arene, and is attributed to the inductive effect of chromium tricarbonyl unit. Now, these so that means that electrophilic reaction sort of occurs, but occurs very slowly, and that is because of the inductive effect of the chromium tricarbonyl unit, whereas nucleophilic substitution occurs readily. And this is best explained by the slide shown over here, where one sees that chlorinated benzene with chromium tricarbonyl and sodium methoxide and methanol giving OMe in presence of the halide, methoxybenzene, chromium tricarbonyl, and the rate of the reaction is similar to that of paranitrobenzene. Rate of the reaction is similar to para-nitrochlorobenzene. Another interesting thing is that the redetermining step is the endo loss of halide ion. The reaction proceeds via eta 5 cyclohexadienal ring which means that nucleophilic attacks over here and it becomes a diene and aromaticity is lost, and the RD step is endo loss of the halide ion. So, that sort of suggests that when the nucleophile attacks adds over here, the aromaticity is lost and it just becomes a hexadiene with OMe on the top and the chlorine on the bottom face, and the loss of the chlorine resulting in the gaining of the aromaticity and methoxy occurs via chlorine being lost from the bottom face or the endo face, which is sort of the most slowest step of the reaction and hence is the rate determining step of this reaction. Similarly, another example of this nucleophilic substitution reaction is shown over here with this amine on this fluorobenzene derivative. R2NH plus this is anion chromium which loses HF to give this dialkyl aniline, dialkylamine bound chromium tricarbonyl. Another example in this reaction is the treatment of lithium CH2CN to this O-methoxy di-O-methoxy complex. This is explained in this beautiful example. Arene, OMe, chromium, CO, that reacting with Li CH2CN giving this nucleophilic attack occurring on CnH2 O Me O Me chromium CO, which in presence of iodine gives this tri-substituted derivative of benzene with CH2 CnO Me. And if one looks at it, it is kind of obvious that the nucleophilic attack occurs in the exo orientation. The nucleophilic attack occurs at exo orientation. Another interesting example involves the reaction of trimethoxybenzene with chromium tricarbonyl, and the beauty about this reaction is that the attack of sigma donor pi acceptor ligands displaces Arene ring. So, this is kind of an interesting reaction in which the attack of sigma donor pi acceptor ligand displaces Arene ring. Usually we see this other way around, that Arene rings displaces sigma pi donor ligands. For example, metal carbonyl by reaction with Arene gives Arene metal carbonyl complexes, but here this is the other way around than what we usually see. So, we have trimethoxybenzene 1,2,3 trimethyl benzene, chromium carbonyl plus 3 PF3 at elevated temperature 140 to 150 degree centigrade, giving chromium tricarbonyl PF3 and a facial isomer is obtained in this case. So, with this I am going to conclude today's lecture, in which we have begun by discussing the preparative methods available for preparation of these Arene metal carbonyl complexes. To begin with, we had seen two other new methods for preparing these Arene metal carbonyl complexes, and one such method involved the direct reaction of metal carbonyl halide with arenes in presence of AlCl3, and the other was simple arene exchange reactions. In addition to that, we have looked into the structure of various metal arene carbonyl complexes, and what we had seen is that a large diversity is observed from the most common eta 6 bound complexes to eta 2 bound dinuclear as well as eta 2 bound trinuclear complexes have been discussed. In addition to that, we have also looked into the reactivity of arene metal carbonyl complexes, and we saw that depending on the part of the ring, the reactivity differs. And to begin with, what we saw that electrophilic substitution reactions, though possible, are kind of slower or less facile than that of the free arenes. However, nucleophilic substitution are considerably more facile, and these nucleophilic substitution occur from the exo phase, resulting in the loss of aromaticity of the ring, followed by the gain of aromaticity and the loss of the group. We have taken a look at several examples of these nucleophilic substitution reaction, and then to end with today's talk, we have also seen that sigma pi donor can also displace arene from arene metal carbonyl complexes, which is usually the other way around that we have studied so far at elevated temperatures. So, with this I conclude today's lecture. Some more discussion still remains on this metal arene metal carbonyl complexes, which we are going to take up in the next lecture. Until then, I thank you again for patiently being with me for this lecture, and I look forward to take the next lecture discussing on more of these arene metal carbonyl complexes and other topics. Till then, goodbye and thank you.